picture the scene for a second. You're cruising down the highway in a state-of-the-art electric vehicle.
Right, perfect weather. Maybe your favorite playlist is on.
Exactly. The climate control has the cabin at a perfect 72 degrees, and you're just comfortably traveling at highway speeds. From the driver's seat, everything is just serene, right? It feels totally effortless.
But underneath you, it is a completely different story.
Oh, absolutely. Right beneath your feet, hidden under those floorboards and shielded by all that heavy steel and insulation, there's this incredibly intense, invisible war being fought every single millisecond. I mean, we tend to think of a modern EV as a car, but it's really much more accurate to describe it as a rolling supercomputer that just happens to have wheels.
Yeah, that's exactly what it is. And at the absolute center of that digital nervous system is your battery management system, or the BMS.
Right. And that BMS is constantly chattering. It's firing off thousands of data packets a second to the rest of the car. It's monitoring cell temperatures, balancing voltages, calculating power limits. Under normal conditions, it is this flawless symphony of digital communication.
But of course, today we're talking about when things are not normal.
Exactly. Here is the scenario we are going to explore today. What happens when that internal network gets so noisy or so corrupted by, say, electromagnetic interference or microscopic physical damage that the car's brain decides the absolute safest thing it can do is to just completely sever its own communication?
It's a really profound engineering problem. And, what you're describing there isn't a glitch. It's not a mistake. It is a highly specific, deliberately engineered response to a catastrophic communication breakdown.
Which is wild to think about. The car is breaking its own connection on purpose.
Right, because when an electronic control unit starts blasting corrupted data at highway speeds, it threatens to overwhelm the entire vehicle's internal network. So the system has to make this life-or-death calculation in a fraction of a second. It must isolate itself to save the whole car.
And that self-isolation is our entire mission for today's deep dive.
Yeah.
We're going to execute a really intense, highly technical teardown of one specific diagnostic trouble code. It's called U0073, which is otherwise known in the engineering world as CAN bus-off.
Yeah, and we need to stress that this is not just a loose wire making your radio flicker or a software bug that, delays your touchscreen.
Right, this is serious. This is a network-level paralysis fault directly within the high-voltage power battery system's electrical circuit and communication layer.
To truly understand the magnitude of this U0073 code, we really have to trace its life cycle across 5 distinct dimensions of automotive engineering.
Let's lay out the roadmap for that.
Sure. So we'll start at the microscopic root causes, analyzing what actually breaks down on a physical and electrical level. Then we'll examine the software architecture, which is the digital safety net that tries to keep the vehicle under control when this paralysis actually hits.
And from there, we move into the preventative engineering design, right? The DFMEA.
Exactly. We'll look at how engineers build hardware defenses against it in the DFMEA. Then we move to the factory floor, the PFMEA, to see how they manufacture millions of these systems without a single microscopic failure. And finally, we'll dive into the DVP&R.
The torture testing.
Oh, absolutely brutal torture testing. The physical tests that engineers put these components through to validate the final product before it ever touches a public road.
So, whether you are an automotive engineer, a tech enthusiast, or honestly just someone who occasionally drives a car, stick with us. Because understanding this single diagnostic code is basically a complete masterclass in how modern engineering balances high-performance technology with these unforgiving, life-saving safety constraints.
It really is.
So let's start with the rules of the road. How does a car's internal communication network operate? And how does it actually break down to the point of total paralysis?
Well, the foundation of this entire conversation is a protocol governed by the ISO 111898 standard. It's known as CAN, or Controller Area Network.
And this isn't exactly new technology, right?
No, not at all. The CAN bus was originally developed by Bosch back in the 1980s, but it was designed specifically for the harsh, electrically noisy environment of automobiles. It's essentially a shared digital highway where every computer module in the car can broadcast and listen to messages.
Okay, so a shared highway. But the U0073 code we're talking about, it isn't like a dropped cellular signal when you go through a tunnel.
No, it is a highly calculated self-isolation mechanism built directly into the physical rules of that CAN standard. When the battery management system realizes that it's no longer transmitting valid data, that it's actually polluting the shared network with garbage data, it physically disables its own transmitter.
It just unplugs itself.
It takes itself completely offline to prevent the rest of the vehicle's network from crashing.
I always think that's like a sophisticated dinner party. Everyone is gathered around a table having this polite, organized conversation, and suddenly one guest begins to experience a severe breakdown. They realize they are just screaming incoherently at the top of their lungs, disrupting the entire room.
That's actually a great analogy.
Right. But crucially, they still have just enough presence of mind to run into the bathroom, lock the door from the inside, and isolate themselves so the rest of the guests can continue their evening in peace.
It's a surprisingly apt way to visualize it, because by locking itself in the bathroom, that compromised guest prevents a cascading panic across the whole house.
Which would be disastrous in a moving car.
Exactly. In the context of a modern EV, if the BMS kept screaming corrupted garbage data onto the network, the vehicle's central computer, the vehicle control unit, or VCU, might misinterpret a scrambled temperature reading as a command to suddenly accelerate or suddenly slam on the regenerative brakes. The isolation is mandatory.
But I need to stop and ask a fundamental question about how a computer thinks here. Because how does the screaming guest actually know they are screaming? I mean, if the internal communication chip is broken or the network is corrupted, how does the system maintain the self-awareness to realize, hey, I'm sending out garbage data, I need to shut my own mouth?
Right. That self-awareness is driven by a very strict, built-in accounting mechanism inside the physical silicon of the CAN controller. Inside every node on the network, there are two crucial hardware trackers.
Yep.
You have the transmit error counter, or TEC, and the receive error counter, or REC. The system is constantly obsessively checking its own homework. It looks for specific, mathematically defined anomalies. Our sources highlight several types, like a stuff error, a form error, a CRC fault, or just a standard bit error.
Let's not gloss over those terms because I think they are key to understanding the sheer speed of this system. What exactly is a stuff error? I'm assuming it has absolutely nothing to do with stuffing a Thanksgiving turkey.
Far from it, yeah. A stuff error relates to a rule in the CAN protocol called bit stuffing. To ensure all the computers on the network stay perfectly synchronized, the CAN standard mandates that you cannot have more than 5 identical bits in a row.
Okay, so no 6 ones or 6 zeros in a sequence.
Exactly. If the data naturally has, say, 6 ones in a sequence, the transmitting hardware will automatically stuff an opposite bit of 0 into the stream just to break it up and keep the clock synced.
And the receiving side knows what to do with that.
Yeah, the receiving computers know to just ignore that stuffed bit, but if a computer actually sees 6 identical bits in a row, it instantly knows the rule was broken. That is a stuff error.
Ah, I see. It's a structural rule. And I'm guessing a form error would be something similar.
Precisely. A CAN message has a very specific architectural frame. So certain bits must always be a 1 and certain bits mark the end of the message. If the rigid format of that frame is violated, that's a form error. And then, of course, you have a CRC fault, which stands for cyclic redundancy check.
Right, the CRC is basically a complex mathematical proof attached to the end of the data packet. It's sort of like a digital wax seal on an envelope. If the math doesn't perfectly match the data when it arrives, it means the envelope was opened or scrambled in transit, and the system rejects it.
Exactly.
Yeah.
Now, every single time one of these structural or mathematical errors occurs while the BMS is trying to talk, that transmit error counter, the TEC, ticks upward. And the ISO standard imposes a hard, absolute, non-negotiable limit for this counter, which is 255.
Wait, 255 errors? That sounds incredibly low. I mean, if the battery management system is sending thousands of messages a second to coordinate the motors and the charging, hitting 255 errors would happen in, what, a fraction of a second?
Oh, it happens in mere milliseconds. The system moves through phases as that counter ticks up. At first, it enters a state called error passive.
What does that mean?
It means it knows it's struggling to communicate, so it stops sending active error flags that interrupt other modules, but it keeps trying to push its data through. However, the very microsecond that TEC hits the absolute limit of 255, the internal state transitions to bus off.
And it shuts down.
The physical transmission hardware is literally disabled. The software throws the U0073 code, and the BMS is entirely severed from the vehicle's communication bus. The door to the bathroom is locked.
Okay, so the digital mechanism makes perfect sense. The counter hits 255, the door locks. But I want to pull this out of the digital realm and into the physical car. Because computers don't just spontaneously generate bit stuffing errors for fun, right?
Mhm.
What is the physical real-world trigger that makes the data so mangled that the counter explodes to 255?
Right. This is where we get into the deep electrical physics of the car. The sources identify four primary, deeply physical root causes. And the first one relies on fundamental wave mechanics. It involves a missing terminal resistor and the creation of standing waves on the network wire.
Standing waves, like when you are making waves in a swimming pool and they bounce back off the wall.
That is actually a perfect physical analogy for what is happening electrically. The CAN network topology relies on a very specific electrical balancing act. At the two extreme physical ends of the network wire, engineers place two 120 ohm terminal resistors.
Okay, 120 ohms each.
Right. And because these two 120 ohm resistors are wired in parallel across the network, the total electrical resistance, the impedance of the entire network, drops to exactly 60 ohms.
So the whole system is tuned to operate in a strict 60-ohm environment.
Correct. This 60 ohm environment is perfectly tuned to allow high-frequency digital signals, which travel as electrical voltage pulses, to move cleanly from one end of the car to the other without any distortion.
But cars aren't perfectly clean environments.
Exactly. Consider the physical environment of a car.
Right.
It hits massive potholes, it vibrates constantly over washboard dirt roads, it experiences severe temperature swings. So what happens if a microscopic solder joint holding one of those 120 ohm resistors finally snaps off the circuit board?
Oh, wow. You lose half your parallel circuit, which means the impedance of the network instantly jumps from 60 ohms back up to 120 ohms. The tension on the tightrope just changed violently.
Exactly. And when that high-frequency electrical signal travels down the wire and hits that sudden unexpected change in impedance, it doesn't just absorb into the end of the wire. Because the electrical characteristics are mismatched, a large portion of that signal's energy reflects backward.
Just like the wave hitting the wall of the pool.
Yes, it bounces off the broken end of the wire and rushes back towards you.
And as it bounces back, it's going to crash head-on into the new data that the computer is actively trying to send down the wire.
Yes, and when the forward-moving data waves collide with the backward reflecting waves, they create a standing wave. In electrical terms, this standing wave severely distorts the physical voltage levels on the wire.
It just scrambles the whole signal.
The clean, square shape of the ones and zeros becomes a garbled, chaotic mess. The receiving computers can't read the stuffed bits, the CRC math fails, the errors skyrocket, the counter hits 255, and within milliseconds, the system goes bus off.
That is just incredible. A microscopic resistor falls off a board in the trunk, an electrical wave bounces backward like water in a pool, and the entire battery management system isolates itself. So what is the second physical cause?
The second cause is much more brutal and straightforward. It's physical shorts and wire damage. To protect against standard noise, the CAN bus uses differential signaling across two wires, logically named CAN high and CAN low.
Differential signaling. So rather than sending a voltage relative to the car's ground, they send signals relative to each other.
Exactly. They idle at a normal differential baseline of about 1.5 volts.
So they are meant to mirror each other perfectly.
They are. But a wiring harness runs all throughout the heavy steel chassis of the car. If the protective plastic insulation on those wires gets rubbed away, say they weren't clipped down properly at the factory and they've been vibrating against a sharp metal edge of the chassis for 3 years, the raw copper is exposed.
And if that touches metal, it's game over.
Right. If that exposed copper shorts out to the grounded chassis or shorts to a 12-volt power line, or even if the CAN high and CAN low wires just short to each other, that delicate 1.5-volt differential is instantly destroyed. The shape of the electrical signal is flattened out or spiked beyond recognition. The data envelope collapses.
So that's pure mechanical trauma. The physical road basically destroying the physical wire. Now, earlier you mentioned electromagnetic interference. I know EVs have massive electrical motors, but how does an electric motor cause a digital communication network to crash? Doesn't the plastic insulation protect the wires from that?
This is the third physical cause, and it is a massive challenge specifically for electric vehicles. It's EMI, or electromagnetic interference, generated by the traction motor inverters.
Why the inverters specifically?
Well, to make the car actually move, the inverter has to take the smooth, steady, direct current, the DC power from the battery, and chop it up into an alternating current, or AC, to spin the magnetic fields in the motors.
Right, because the battery is DC, but the motors need AC to create the rotating magnetic pull.
Exactly. To do this, the inverter uses high-frequency solid-state switches. In older EVs, they used IGBTs, which are insulated gate bipolar transistors. In newer, high-performance EVs, they use silicon carbide components.
So they're switching on and off.
Think of these as massive digital bouncers that open and close the gates of electrical power thousands and thousands of times every single second. This switching happens with incredible violence. We are talking about massive amounts of voltage changing in microseconds, what engineers call dV over dt, or delta voltage over delta time, and massive amounts of current changing simultaneously d over dt.
So you have this box under the hood that is violently slicing hundreds of amps of electricity thousands of times a second. It must be radiating an insane amount of energy.
It creates a massive, invisible strobe light of electromagnetic noise. If the shielding on the delicate communication wires is compromised, or if a grounding strap is slightly loose, or if a factory worker accidentally routed the low-voltage CAN wire just a few inches too close to the high-voltage power cables, that electromagnetic strobe light blasts right through the standard plastic wire insulation.
The plastic doesn't stop it at all.
No, it introduces what is called common mode noise.
Common mode noise because it hits both the CAN high and CAN low wires at the exact same time from the outside.
Yes. It essentially raises the voltage of both wires simultaneously, drowning out the quiet, delicate differential conversation happening between them. It is the equivalent of trying to have a nuanced, whispered conversation while standing next to the speaker stacks at a heavy metal concert.
This is a great visual.
Yeah, the noise floors the signal, the data is lost, and the transmit error counter hits 255.
Okay, so we have standing waves, rubbed wires, and electromagnetic heavy metal concerts. What is the fourth root cause?
The fourth cause is insidious because it happens entirely inside the solid components. It's microcracking in the PCBA vias. Inside the physical computer modules, the printed circuit board assemblies are made of multiple layers of fiberglass and copper.
Right, they're layered.
To connect a circuit on the top layer to a circuit on the bottom layer, they drill a microscopic hole through the board and electroplate the inside of the hole with a very thin layer of copper. That copper-plated hole is called a via.
So it's essentially a tiny microscopic tunnel connecting the floors of the computer board.
Exactly. Now, over the 10 or 15-year lifespan of a vehicle, it goes from freezing winter nights at -20 degrees up to boiling summer days parked on black asphalt where the internal components might reach 80 degrees Celsius.
Expanding and contracting.
This happens over and over, thousands of times. The fiberglass material of the board and the copper plating inside that via expand and contract at different rates as they heat and cool. This is called the coefficient of thermal expansion mismatch.
Because they are different materials, they're essentially fighting against each other every time the temperature changes.
And eventually, that constant physical stress can cause a microscopic, invisible crack in the thin copper plating of that via. The tunnel collapses, the connection is severed on a microscopic level, the electrical resistance shoots up, the network connection dies, and the U0073 code is triggered.
Okay, so we've established that the physical environment inside an EV is incredibly hostile. A missing resistor, a rubbed wire, invisible magnetic interference, or a microscopic crack in a board triggers this cascade, and the battery management system locks its door to protect the network.
Yes.
But here is where I struggle with the logic, and I need to push back on this safe state idea. You're telling me the car decides the absolute safest thing to do at 70 miles an hour on a crowded highway is to completely blind the central computer to the battery status.
It sounds crazy, I know.
How is losing all your power data, suddenly flying completely blind, safer than just trying to ignore a few corrupted signals?
It is a totally counterintuitive approach, but you have to think about what corrupted data actually means to a 2-ton vehicle traveling at highway speeds. It's not just a skipped track on a CD or a bloomy pixel on a screen.
Right.
If the Central Vehicle Control Unit, the VCU, is receiving garbage data, it might interpret a scrambled temperature reading as a command to deploy full torque to the rear wheels. It might interpret a bit error as a command to shut down the cooling pumps while the battery is at critical heat. Unpredictable data is infinitely more dangerous than zero data. When you have zero data, you can execute a predictable, controlled shutdown.
Okay, I see your point. Predictable failure is safer than unpredictable behavior.
Yeah.
But that brings us to the safety architecture. If the BMS has locked itself in the bathroom, the VCU is suddenly flying blind. How does the car not just spiral totally out of control the moment the battery stops talking?
This is where we see the absolute brilliance of automotive functional safety engineering. To prevent a catastrophic loss of control, engineers employ a framework governed by an international standard called ISO 26262. Specifically, they use end-to-end, or E2E, safety logic.
ISO 26262 is essentially the Bible for keeping automotive electronics from doing things they shouldn't, right?
It is the global standard for the functional safety of road vehicles, and a core pillar of that standard is timeout cascade protection. Remember we talked about those data packets having CRC
The
checks?
mathematical wax seals.
Right. They also have rolling counters.
Hmm.
The central VCU is expecting a heartbeat message from the battery system at very specific rigid intervals. It expects message number 1, then message number 2, then message number 3.
And if it misses one?
If the VCU misses that heartbeat, or if the counter skips a number, for a critical threshold, typically just 500 milliseconds, half a single second, it instantly assumes the worst-case scenario. It initiates a cascade protection protocol, immediately cutting power and lighting up the dashboard with warnings to alert you, the driver, that something is critically wrong.
Oh, wait, hold on. 500 milliseconds, half a second. Let's unpack this quick recovery concept.
Mm.
Because shutting down a car's propulsion on the highway because of a split-second glitch seems incredibly dangerous in itself.
It is a delicate balance, for sure.
If I hit a bump and the network drops for half a second, I lose my momentum, I lose regenerative braking, I become a hazard to the semi-truck right behind me. That seems far too aggressive.
And the engineers completely agree with you. That is why they do not just give up immediately. Before that half-second timeout fully commits the vehicle to a hard shutdown, the software architecture utilizes an auto-recovery strategy, which is governed by another standard called AUTOSAR CAN-SM.
So it tries to save itself.
They build in a window for the system to try and fix itself invisibly. We call this the quick recovery phase.
How quick is quick?
Just 50 milliseconds.
Yeah.
50 milliseconds after the BMS isolates itself and enters the bus-off state, the internal software forces a hardware reset of the scan controller chip. It reboots itself and quietly sends out a tiny test message to test the waters. It's trying to reconnect and clear the error without you, the driver, ever knowing anything went wrong.
50 milliseconds. That is literally faster than the human eye can blink. So the system crashes, locks the door, realizes it's locked the door, reboots the silicon, cracks the door open, whispers a test message to see if the coast is clear, and tries to rejoin the party. All before the human brain can even process a thought.
Precisely. And if the original fault was just a fleeting temporary spike of electromagnetic interference, maybe you drove directly over a massive underground power cable or a passing truck keyed a massive CB radio, the quick recovery works perfectly. The test message gets through, the network is restored, the heartbeat resumes, and your drive is completely uninterrupted.
But what if it isn't a passing radio wave? What if the cause is one of those physical issues we discussed? What if that wire is permanently rubbed bare against the steel chassis?
Then the 50 millisecond test message is going to hit that physical short circuit. The resulting data collision will cause the transmit error counter to instantly skyrocket straight back to 255, and the system is going to violently crash again.
And since it's programmed to recover, it's just going to try again, right?
Yeah.
Another 50 milliseconds later.
It will try, but it cannot do it infinitely. And the reason why is deeply tied to the physical hardware. If the software just kept executing that 50 millisecond quick recovery in an endless rapid-fire loop, the central processing unit would consume all its processing bandwidth just rebooting.
It would just get stuck in a loop.
Right. And more importantly, the physical transceiver chip, the actual piece of silicon pushing voltage onto the wire, would overheat. Pushing current into a dead short creates massive heat. If it tries too fast for too long, the transceiver would suffer a thermal crash and physically melt down on the board.
It would literally burn itself alive trying to reconnect.
Exactly. So the software is programmed with a hard limit. After 5 failed quick retries, it gives up on the fast approach. It falls back to a slow recovery cycle.
That was slow.
Instead of trying to force a connection every 50 milliseconds, it pulls back and waits a full 2,000 milliseconds, 2 full seconds between attempts. It takes a digital breath. It waits for the physical hardware to cool down, hoping that whatever caused the fault might resolve itself. For example, maybe that loose connector that vibrated out of position will vibrate back into place on the next bump.
Okay, so it tries the rapid-fire approach and fails. It steps back, tries a slow approach, and fails. What does this safe state logic actually look like when all the recoveries totally fail and the car realizes, I am permanently blind, the battery's gone?
The response depends entirely on what the vehicle is doing at that exact moment. Let's look at two distinct scenarios. First, the pre-charge phase. Let's say your car is parked in your driveway. You get in, you put your foot on the brake, and you hit the start button. Before the car ever connects the massive 400-volt battery to the electric motors, it executes a rapid self-check of the entire network. If it detects a U0073 communication fault during the startup phase, the safety logic refuses to close the main high-voltage relays.
It just acts like a dead car.
Exactly. It simply will not let you start the vehicle, and it will not let you plug it into a charger. It is hard stop. The vehicle is immobilized safely in your driveway. It's an inconvenience, certainly, but a perfectly safe one.
Right, you're going to be late for work, you're calling a tow truck, but you aren't in danger. What about the terrifying scenario, the one we started with? You are already on the highway driving 70 miles an hour.
Right. If you are actively driving, the slow recovery cycle keeps trying in the background. But if a continuous 5-second timeout window passes without any successful recovery, the system accepts its reality. The communication network is completely permanently paralyzed. At this exact moment, the BMS Level 2 safety logic takes over.
Level 2 safety logic.
Yeah, it enters a highly structured phase known as the fault-tolerant time interval, or FTTI. In this specific architecture, the FTTI has a rigid, unforgiving deadline of exactly 2.0 seconds to save the vehicle and its occupants.
2.0 seconds. The countdown clock starts. What on earth happens in those 2 seconds? Do they just blow a fuse?
They cannot just blow a fuse or instantly sever the high-voltage cables. Think about the physics. The electric motors might be pulling hundreds of amps of current to maintain that highway speed. If you simply rip the battery contactors open under that kind of massive electrical load, the electricity will try to bridge the gap.
It'll arc.
It will pull a massive electrical arc, essentially a sustained plasma fire, right inside the relay box. It would weld the contacts shut or cause a catastrophic fire. So you can't just pull the plug on a system pulling that much juice. It has to be staged. Exactly. Instead of pulling the plug, the BMS forcefully steps in and executes a soft cutoff command. Even though it can't talk to the VCU, it uses dedicated hardwired backup lines to gracefully command the motor inverters to reduce their current draw down to 0 over the course of roughly 1 second. You, as the driver, will feel the car suddenly lose all its power.
The pedal just goes dead.
The pedal goes dead. But once the software verifies that the electrical load has reached 0, that no current is flowing, it then, and only then, forcefully rips the high-voltage relays open, physically isolating the massive chemical battery from the rest of the car.
Forcing it into the safe state.
Yes. The vehicle is forced into its ultimate safe state. You lose propulsion, yes, but the battery is isolated, the fire risk is mitigated, the dashboard is screaming at you to pull over, and you retain your 12-volt systems, your steering, your brakes, allowing you to safely coast to the shoulder of the highway.
That choreography is breathtaking. From a tiny VAC cracking under thermal stress, to a digital counter hitting 255, to an invisible 50-millisecond reset, to a 5-second realization of network death, to a 2-second grace period where it perfectly powers down the motors before pulling the plug. It is a flawless digital ballet.
And it is all designed to happen automatically without requiring any input or decision-making from the human driver, because human reaction time is simply too slow and too panicked to manage an electrical fault of this magnitude.
Which brings us to the preventative side of the equation. We know the code, we know how the errors build, and we know the incredibly intricate safety nets that try to catch you when the system falls. But as engineers, the goal isn't just to build a good safety net. You want to prevent the system from falling in the first place.
Of course.
When they're drawing up the blueprints, in the design failure mode and effects analysis, the DFMEA, how serious is this U0073 code considered?
It is considered one of the most critical. In the DFMEA methodology, every potential failure is graded. Our sources note that this specific U0073 failure mode is rated as a severity 8, a high AP action priority failure.
Out of 10-point scale.
Yes, on a scale of 1 to 10. A severity 8 implies that the failure results in a complete loss of primary vehicle function, in this case vehicle propulsion, without any prior warning to the driver.
Why not a 9 or a 10?
It doesn't score a 9 or a 10 because it doesn't immediately disable the physical safety systems like the mechanical brakes or the steering rack, but losing propulsion at highway speeds is still a critical high-priority failure mode. Engineers must design aggressive defenses against it from the very first CAD drawing.
I always think of this phase of engineering like designing a bank vault. You don't just install a really loud alarm system and hope bank robbers don't try to break in. You build thicker concrete walls. You make the physical structure itself impenetrable. So my question to you is, how do you build a thicker wall on a microscopic computer chip to defend against things like transient noise and standing waves?
You build microscopic shields directly into the physical trace lines of the circuit board. The very first line of defense at the physical layer is the integration of TVS arrays. TVS stands for transient voltage suppression. Imagine these components as extremely fast-acting pressure relief valves for electricity, placed right at the front door of the CAN, high and low differential lines, just before the signals enter the delicate transceiver chip.
What exact scenarios are they protecting the chip from?
Massive, sudden, unexpected high-voltage spikes. Let's look at a phenomenon called a load dump. A load dump happens if a high-power component, like a heavy-duty alternator or a massive regenerative braking motor, is suddenly disconnected from the battery while it is still actively pumping out energy.
Where does that energy go?
That massive amount of electrical energy suddenly has nowhere to go, so it surges backward, creating a massive voltage spike that cascades through the entire vehicle's electrical system. Another scenario is back EMF electromotive force. When you suddenly cut power to a large inductive component like a motor coil, the collapsing magnetic field creates a violent backward spike of voltage.
And if that hits the chip,
If one of those high voltage spikes manages to hit the delicate 1.5 volt CAN bus transceiver, it will instantly blow a hole right through the silicon.
so the TVS array acts like a microscopic lightning rod.
That is an excellent analogy. When that massive surge of voltage hits the line, the TVS diodes detect it. Through a process called avalanche breakdown, they instantly change their electrical properties and clamp the surge down to safe levels. And they do this in mere nanoseconds.
Billions of a second.
Yes, they shunt all that dangerous, destructive energy straight to the vehicle's ground plane before it can even touch the sensitive communication chips. It is an incredibly robust, incredibly fast first line of defense.
Okay, so the lightning rods catch the massive destructive spikes. But earlier, you spent quite a while talking about electromagnetic interference, the EMI, that common mode noise screaming from the motor inverters, switching thousands of times a second. A lightning rod doesn't stop ambient noise. How do you block a heavy metal concert?
For the EMI noise, engineers don't just build a shield, they build a literal physical wall between the networks. They use a technique called galvanic isolation.
Galvanic isolation.
Ah,
I've actually heard this term used in super high-end audiophile equipment to prevent humming noises. It essentially means there is zero physical electrical connection between two circuits, right? The electrons literally cannot pass from one side to the other.
that is exactly right. The sensitive low-voltage communication network and the noisy high-voltage battery network are kept entirely physically separated on the circuit board. To allow them to still talk to each other without touching, engineers use high-impedance magnetic transformers or optical isolator.
How does an optical isolator work?
Let's visualize an optocoupler. The electrical data signal comes in from the noisy side, hits a microscopic LED, and turns into a tiny flash of light. That light crosses a physical gap of empty space inside the chip, hits a photosensitive light sensor on the clean side, and turns back into an electrical signal.
That is wild. They literally translate the data into photons of light, so the electrical noise cannot cross the bridge.
Exactly. Because common mode electrical noise, no matter how loud or violent, cannot travel across a physical air gap. The technical specifications indicate this galvanic isolation barrier is robust enough to withstand over 3,000 volts RMS.
That is a massive barrier.
It completely, utterly blocks the electrical conduction of that common mode noise between the dirty, high-voltage switching loops and the clean, sensitive, low-voltage communication network.
It is exactly like putting two people in completely separate soundproof rooms with a thick pane of bulletproof glass between them and having them communicate by flashing flashlights at each other through the glass. The screaming from the heavy metal concert next door simply cannot vibrate through the glass.
And to reinforce that glass wall even further, they also deploy common mode chokes on the wire traces. A choke is an inductive component, a coil of wire wrapped around a magnetic core. Because of the physics of inductance, a choke allows the intended differential signals, the CAN high and CAN low voltages moving in opposite directions, to pass through the coil very easily.
But it blocks the noise.
Right. It presents a massive high impedance roadblock to common mode noise, which is trying to travel down both wires in the same direction at the same time. The choke physically filters out the noise before it can reach the chip. Furthermore, for these hypercritical vehicle control signals, they don't just rely on a single isolated CAN bus, they utilize CAN-FD dual-channel hardware redundancy.
So they double up on the hardware.
Yes, if one entire physical channel gets corrupted by a severed wire, the second independent channel is already carrying the exact same data, ensuring the message always gets through.
Okay, the TVS diodes clamping voltage, the optical isolation turning data to light, the magnetic chokes blocking the noise, the dual-channel redundancy. It is an absolute fortress of design.
Mm-hmm.
But as I was reading through the source material on the DFMEA architecture, there was one detail that absolutely blew my mind. It's about how the internal battery boards talk to each other, the bidirectional ring topology. Can you explain the genius of what is going on there?
It is arguably one of the most elegant engineering solutions in the entire system. Inside a large EV battery pack, there isn't just one single computer board monitoring thousands of cells. There's a master controller board and multiple smaller slave boards distributed throughout the pack monitoring different clusters of battery cells.
And normally those are just wired in a line, right?
In a standard architecture, these are connected in a linear line. But in this advanced design, they are connected in a daisy chain formation that loops all the way back around to the master. This is a ring topology.
So board A talks to board B, B talks to board C, C talks to board D, and then D has a wire that loops all the way back to board A. A complete closed circle.
Correct. Now let's imagine a worst-case physical scenario inside that sealed battery pack. The vehicle hits a massive pothole, creating an immense violent vibration. One of the physical metal pins in the connector linking board B and board C snaps completely in half. The physical connection is totally broken.
In a normal linear daisy chain, board C and board D would instantly go dark. They are cut off from the master. The master controller suddenly loses sight of half the battery pack's temperatures and voltages. That is a catastrophic failure that would trigger an instant vehicle shutdown.
In a standard network, yes, that's exactly what would happen. But in this bidirectional ring topology, the software running the master controller is incredibly smart. Within microseconds of that metal pin breaking, the master controller realizes that its data messages are no longer completing the full loop.
It sees the break.
It analyzes the returning data and instantly identifies exactly where the physical break occurred between B and C. It then dynamically instantly reconfigures the network routing logic. It sends the data for board A and board B down the normal forward path. But to reach board C and board D, it sends the data backward through the other side of the loop.
That is just brilliant. The data hits the broken bridge, turns around, and takes the back road.
Exactly. And this dynamic rerouting happens so fast that the system maintains 100% data synchronization without dropping a single watt of power, without throwing a single dashboard warning, and without missing a single millisecond of operation. The human driver has absolutely no idea that a physical piece of metal just snapped in half inside their battery pack. The system just intelligently routes around the physical damage and keeps the car moving safely down the road.
That is the definition of robust engineering. So we have designed a perfect impenetrable digital vault on a computer screen. The blueprints are flawless. But how do you actually build 1 million of these vaults in the real world without a single worker dropping a screw or a robotic arm missing a solder joint? That brings us to the factory floor and the process failure mode and effects analysis, the PFMEA.
This is where theory meets reality.
Exactly. We are talking about controlling human and machine error at a massive industrial scale. Engineers call these the 5M1E variables: man, machine, material, method, measurement, and environment. It sounds like an utterly impossible task. How do you catch a microcrack in a via or a missing drop of solder before the car is even fully built?
It requires an obsessive, almost paranoid level of quality control across the entire manufacturing line. The modern EV factory isn't just assembling parts, it's an environment actively hunting for microscopic defects. To catch those cold solder joints or potential micro cracks before the circuit board is ever enclosed in a case, they employ incredible vision systems. Every single printed circuit board goes through 100% 3D SPI solder paste inspection and 3D AOI automated optical inspection.
Let's dig into that. When you say 3D inspection, it's not just a high-resolution camera taking a flat picture, right?
Yeah.
How does a machine measure solder in 3D?
They use highly advanced phase shift profilometry or moire fringe projection. The machine projects microscopic patterns of light across the circuit board. By measuring how those patterns of light bend and distort over the blobs of gray solder paste, the laser sensors map the exact height, volume, area, and shape of every single pad of solder on the board.
So it builds a complete 3D topographical map of the circuit board in seconds.
Yes. And the tolerances are microscopic. If a single pad on a communication chip has even 2% less solder paste volume than the strict engineering specification requires, the machine instantly flags it and rejects the board.
Just for 2%.
It does this because the data proves that a 2% deficiency today could lead to a cold solder joint cracking under thermal stress 5 years down the road. But they don't just rely on non-destructive optical checks, they also perform brutal destructive testing. On a regular statistical basis, quality control engineers will take a perfectly good, fully assembled, expensive circuit board right off the production line, and they will physically destroy it. They cut it in half, right through those tiny microscopic vias we discussed earlier.
They destroy a perfectly good part just to check it. What exactly are they looking for when they cut it open?
They are performing metallographic cross-sectioning. They take the sliced via, embed it in resin, polish it to a mirror finish, and put it under a scanning electron microscope. They are measuring the exact micrometer thickness of the electroplated copper on the inside wall of that tiny hole.
To make sure it's thick enough.
They need absolute physical proof that the chemical electroplating process on the factory floor is currently depositing a thick enough layer of copper to withstand a decade of thermal expansion and contraction without cracking. They destroy one perfect board to statistically guarantee the next 10,000 will survive.
Wow. Okay, so the circuit boards are validated, the vias are thick, the solder is mapped. But earlier, you spent a lot of time talking about the terrifying standing waves caused by a missing 120 ohm terminal resistor. How does the factory ensure those specific resistors are actually installed and not cracked before the massive battery pack gets bolted into the belly of a car?
This relies on one of the most critical automated checks in the entire factory, known as the rigid end-of-line, or EOL, resistance scan. At the very end of the battery assembly line, right before the giant heavy metal lid is bolted onto the high-voltage battery pack, which is the final point of no return for repairs, the entire pack is plugged into a massive automated testing station.
What does the station do?
This station shoots a precise direct current down through the CAN bus communication lines to measure the total DC electrical impedance of the network.
And what exactly is the machine looking for?
It is looking for mathematical perfection. Remember the tightrope. 220 ohm resistors wired in parallel must equal exactly 60 ohms. However, the factory testing equipment has a razor-thin acceptance window. The total impedance must read exactly between 59 ohms and 61 ohms.
A 2 ohm margin of error. That leaves almost no room for contact resistance from the testing cables themselves.
It is remarkably strict. If the machine reads 120 ohms, it instantly deduces that one of those terminal resistors is completely missing, broken in half, or has a cracked solder joint. If the machine reads under 50 ohms, it knows there is a physical short circuit somewhere deep inside the wiring harness.
And if it's outside the window?
If the reading falls anywhere outside that incredibly narrow 59 to 61 ohm window, the battery pack is rigidly intercepted. It triggers factory alarms, the assembly line literally stops moving, and that specific battery is physically barred from moving to the final assembly station. It absolutely cannot, under any circumstances, be put into a vehicle.
It's a hard gate. You don't pass unless your physics are mathematically perfect. But what about the simpler, more human errors? We've talked a lot about micro cracks and standing waves, but what about a worker on the line just not pushing a plastic wire plug in all the way? A loose connector vibrating out while driving over a bumpy road would instantly trigger that U0073 bus-off code, right?
Absolutely, and the automotive industry has spent decades trying to engineer away the loose plug problem. They use specialized automotive connectors with double locking mechanisms, known as TPA terminal position assurance and CPA connector position assurance.
How do those work?
When a human worker pushes a plug together, they have to engage a secondary physical lock, usually a colored plastic tab. That tab physically cannot be pushed down into the locked position unless the primary internal copper pins are perfectly deeply seated.
That's a great physical safeguard. But humans are still humans. Someone gets tired at the end of a grueling 10-hour shift, their thumbs are sore, and they just forget to push the secondary lockdown.
Which is precisely why modern factories do not trust the human operator alone. They build layers of machine verification. First, the automated crimping machines that attach the copper wire to the metal pin are dynamically monitored. The machine measures the exact stroke distance and the physical force of the crimp in real time. If the force profile feels off by a fraction of a newton, it rejects the wire. Then, when the worker on the line actually plugs the connector into the module, there are highly sensitive directional microphones positioned at the workstation. They are running fast Fourier transform algorithms, listening specifically for the high-frequency acoustic snap sound of that plastic lock engaging.
Wait, really? The factory is using microphones to literally listen for the click. How does it filter out all the pneumatic drills and background noise of an industrial factory?
By analyzing the frequency domain, the sound of a plastic locking tab snapping into place has a very specific sharp frequency signature that stands out against the low rumble of factory noise. The system isolates that frequency. And if an acoustic snap isn't enough, there is also a high-speed camera positioned over the workstation.
For visual check.
Exactly. The moment the plug is inserted, it takes a high-resolution, illuminated photograph of the fully engaged lock. That photo is 100% visually archived on a server and permanently tied to the specific VIN, the serial number of that vehicle. If there is ever a warranty claim 5 years later for a dropped communication network, the manufacturer can pull up the exact photo of that exact plug on the specific day it was built to prove it left the factory locked perfectly.
That level of traceability and paranoia is stunning. Okay, so we've laser mapped the solder, cross-section the vias, verified the 60 ohms, listened for the acoustic clicks, and archived the photos. But we still have that massive EMI problem, the common mode noise from the high-voltage power cables we discussed earlier.
Yeah.
How does the factory ensure a tired worker doesn't accidentally zip-tie a delicate, low-voltage CAN wire right next to a pulsating 400-volt power cable?
They manage this through a manufacturing concept called poka-yoke, which is a Japanese term for mistake-proofing. You don't just put up a sign or train a worker not to route the cables close together. You design the physical environment so it is physically impossible for them to make the mistake.
So the design forces the routing.
Right. The low-voltage communication wires are routed through specific, rigid plastic channels and clips molded into the casing. These channels are physically blocked and separated from the high-voltage bus bars by rigid plastic walls, ensuring the communication wires never get closer than 100 millimeters to any high-voltage cable. The physical geometry of the casing forces the separation.
And then finally, before this meticulously assembled battery pack leaves the factory floor, there is one last stress test, right? The EOL stress test.
Yes. Once the pack is sealed and passes all static checks, they hook it up to a massive diagnostic simulator. And then they intentionally attack it. They inject pseudo-random digital noise directly onto the CAN network. They blast the network with excessive data traffic, pushing it to greater than an 80% bus load.
It's a normal load.
To put that in perspective, a normal car operates at maybe a 30% or 40% bus load. Pushing it past 80% creates a massive amount of chaotic data traffic. They hold this agonizing stress test for a full continuous minute. During this minute, the system's computers monitor the bit error rate, or BER. After a full minute of high-load, artificially noisy, high-stress operation, that bit error rate must remain at absolute zero, not a single dropped bit. Only then is the battery allowed to leave the factory.
Okay, so they have engineered an absolute digital fortress. They have manufactured it perfectly, checked the math, listened for the clicks, and stress tested against artificial noise. It seems completely invincible. But that leads us to the final dimension. Because before an automaker lets you, the consumer, drive this car for 10 years, through blizzards and heat waves, over 300,000 kilometers in the real world, they have to actively, aggressively try to destroy it. This is the Design Verification Plan Report, the DVP&R. I like to think of this as the ultimate engineering boot camp. They take the absolute weakest links in the design and weed them out through literal physical torture.
Boot camp is a very apt description. The purpose of the DVP&R phase isn't to pat themselves on the back and prove the system works. The goal is to find exactly where, when, and how it breaks under extreme duress. The first stage of this boot camp focuses on the software's resilience. It's called HI fault injection. HIL stands for hardware in the loop.
How does that work?
They take a real physical production intent battery management system from the assembly line and hook it up to a massive supercomputer simulator. This simulator perfectly mimics the electrical behavior of the entire rest of the car: the motors, the wheels, the dashboard.
So the BMS brain fully believes it is driving a real car down the highway, but it's actually just sitting on a lab bench hooked to a matrix.
Exactly. And while the BMS is happily driving in the simulation, the test engineers step in using a specialized fault injection box. They intentionally and maliciously short out the physical CAN lines. They are acting as an active adversary, trying to force that transmit error counter to overflow to 255.
They're essentially playing the villain, actively trying to crash the system to see how it reacts.
Yes, they trigger the short circuit and they watch the software fight for its life. They use high-speed data loggers to meticulously verify every single step of that AUTOSAR CAN-SM safety net we discussed earlier. They verify that the system detects the short, enters bus off, and attempts that 50-millisecond quick recovery.
And when it fails,
When the test engineers hold the short, they verify the software realizes it failed and correctly switches to the 2,000-millisecond slow recovery. Finally, they verify that after exactly 5 seconds, the software gives up, permanently logs the U0073 code, illuminates the malfunction indicator lamp on the simulated dashboard, and perfectly executes the 2-second soft cutoff to reach a safe state. They have to prove that the software responds exactly as designed under an active, hostile hardware attack.
okay, so the software logic survives the attack. But what about the physical hardware itself? We spend a lot of time talking about those microscopic copper vias cracking under thermal stress, or those tiny 120-ohm terminal resistors snapping off the board. How do you compress a decade of winter freezes and summer heat waves into a lab test to prove they will survive?
You put them in a thermal shock chamber. This is a genuinely brutal piece of industrial equipment. They take the fully assembled printed circuit boards and slam them into a chamber that rapidly cycles temperatures. They drop the temperature to negative 40 degrees Celsius, deep, brittle, freezing winter, and let the board soak in the cold.
And
Then the chamber violently transitions straight up to 85 degrees Celsius, which is baking, oven-like heat. And they do this transition at an incredibly fast, violent rate of temperature change, which is 10 degrees Celsius per minute.
that is violent. That's like taking an ice-cold glass out of the freezer and immediately pouring boiling water into it.
Yeah.
The materials are expanding and contracting so fast, you are practically begging the structure to shatter.
Exactly. The thermal expansion is putting immense shear stress on every single solder joint, every single silicon microchip, and every single copper via. And they don't just do this cycle once or twice. They run this agonizing thermal shock cycle continuously for 500 grueling hours.
Almost 3 straight weeks of being frozen and boiled. And after 500 hours of being tortured like that, what exactly are they looking for to determine if it passed?
They pull the board out of the chamber, let it stabilize to room temperature, and they plug it right back into the impedance scanner. After all that violent expansion and contraction, the total parallel impedance of the CAN network must still rest perfectly within a razor-thin margin of 57 ohms to 63 ohms.
Wow, it can barely drift.
If it drifts even slightly outside that, it means a terminal resistor is failing or a solder joint has fractured. They also take those tortured boards, slice the vias open again, and put them under the electron microscope. The rigid engineering requirement states that any microscopic cracks that have formed in the copper plating cannot exceed 10% of the cross-sectional area of the via. It has to survive 500 hours of thermal violence with less than 10% structural degradation.
It's astounding that anything built out of fiberglass and copper can survive that kind of environmental abuse. But I have another question, another hypothetical what-if scenario for the boot camp. What if the car's traditional 12-volt battery, the one that powers the computers, the headlights, and the radio, suddenly dies or drops in voltage right while this complex U0073 system is trying to save the car?
That is a phenomenal engineering question, and it is exactly what the brownout testing phase is designed to validate. In a real-world scenario, a massive electrical fault in the high-voltage system might cause the 12-volt accessory system to violently dip in voltage. This is called a brownout.
And if that happens during the recovery?
Right. If the computer chips inside the BMS lose their 12-volt power supply right at the exact moment they are trying to execute that life-saving 50-millisecond quick recovery, the silicon could enter a sleep lock. The computer would freeze up entirely, the recovery would fail, and the car would be left in an undefined, highly dangerous state.
The computer basically passes out from lack of oxygen right when it needs to be doing CPR on the network.
Precisely. So in the lab, Test engineers use highly programmable power supplies to intentionally simulate this catastrophic timing. While the BMS is transmitting massive amounts of data, they suddenly artificially drop the input voltage from a healthy 12 volts down to a starving 4.5 volts for exactly 100
They
milliseconds.
intentionally choke off its power supply during a critical operation. How on earth does the hardware survive that?
Through incredibly robust physical hardware design on the board itself, the power traces on the BMS are equipped with components called low dropout regulators, or LDOs, paired with massive energy storage capacitors. Think of these capacitors as tiny reservoirs of electricity.
Like a little battery backup.
Exactly. They act like a miniature, onboard, uninterruptible power supply, a UPS, specifically dedicated to the communication chips. The testing validates that these capacitors hold enough reserve electrical energy to keep the transceiver alive, awake, and fully functioning for at least 50 milliseconds after the main power drops. This reserve energy ensures the chip doesn't trigger an undervoltage lock, allowing it enough time to complete its auto recovery cycle and ensuring a 100% successful digital rescue even while the car's main electrical system is collapsing around it.
It essentially holds its breath underwater just long enough to unlock the door and escape. Just incredible. We are at the very end of the testing boot camp. What is the absolute final validation before they finally stamp this design as ready for mass production and put it in a car you can buy?
The final validation is actually a visually beautiful test. It's called the eye diagram validation. Engineers take the fully assembled, fully tested system and map the raw physical CAN differential signals, the CAN high and CAN low voltages, into a high-speed, high-resolution oscilloscope.
What does it show them?
They set the oscilloscope to overlay thousands and thousands of consecutive data packets directly on top of each other on the screen. Because of the way the ones and zeros overlap, the resulting visual shape on the screen looks exactly like a human eye.
An eye diagram. And what exactly makes a good eye to an engineer?
They are looking for an eye that is wide open, clean, and perfectly symmetrical. The high and low voltage edges of the signals must be incredibly crisp, with absolutely no fuzziness or jitter. The center of the eye has a predefined boundary zone called the eye mask.
And the signal can't enter that mask.
The signal traces cannot touch or cross into this mask. If there were any of those standing waves we discussed earlier bouncing around, or if any common mode EMI noise was sneaking past the galvanic isolation, the lines on the screen would blur. The eye would look sleepy, half-closed, or heavily distorted, cutting into the mask. But if that eye is wide open and pristine after surviving the fault injection, the 500 hours of thermal shock, and the choking brownouts, it proves definitively that the physical layer is absolutely bulletproof. And only then is the vehicle finally cleared for mass production.
Okay, let's step back and summarize this monumental journey we've just been on. We started with the smallest possible failures. A microscopic via cracking inside a fiberglass board undergoing thermal stress, or a tiny terminal resistor vibrating off a circuit board. We saw how that tiny physical failure creates a bounced electrical wave, a standing wave, that severely distorts a delicate 1.5-volt differential signal.
And then the cascade begins.
Exactly. We saw how that voltage distortion forces a digital error counter to tick up to exactly 255, throwing the terrifying U0073 bus-off code and causing the battery management system to deliberately lock itself in the bathroom to prevent the rest of the car's network from crashing.
And then we explored the intricate cascade of software safety logic that takes over, the 50-millisecond invisible reset attempts trying to save the connection, the 2,000-millisecond slow recoveries letting the hardware cool down, and finally, the rigid 2.0-second FTTI grace period where the system gracefully powers down the traction motors and pulls the high-voltage plug to force a safe state and keep the occupants safe.
We looked at the nanosecond hardware defense walls, the TVS diodes acting like lightning rods to clamp load dumps, the optical glass walls of galvanic isolation stopping the screaming common mode noise from the inverters. We walked the factory floor, analyzing the 3D laser mapping of microscopic solder paste, the destructive cross-sectioning of perfectly good boards, the acoustic microphones listening for the snap of a connector, and the rigid 59 to 61 ohm checks.
And we survived the boot camp.
And finally, we survived the 500 hours of thermal torture, the choking power brownouts, and emerged looking at a perfectly open, wide-awake eye diagram on an oscilloscope. It is, frankly, an unbelievably intricate, almost miraculous dance of physics, software logic, and industrial paranoia, all meticulously designed with one singular goal: to keep you safely moving forward.
It really highlights the hidden reality of modern transportation. Modern engineering is not just about making things work when everything is perfect. It is primarily about predicting exactly how things will inevitably fail in a hostile environment and building graceful, invisible safety nets to manage those failures long before they can reach the driver.
It is truly a masterclass in resilient design. But before we wrap up today's deep dive, I want to leave you, our listener, with a final, slightly provocative thought to ponder. We've spent this entire time discussing how a single vehicle acts to protect itself by deliberately shutting its own mouth when its internal network is compromised. It isolates itself to save the car. But as we move rapidly toward the future of V2X, vehicle-to-everything communication, where cars are constantly talking not just to themselves, but to smart city infrastructure, traffic lights, and millions of other autonomous vehicles on the road, what happens when the external city network becomes corrupted?
That is a fascinating question.
Will an entire fleet of autonomous cars experience a simultaneous data cascade? Will they trigger a collective, city-wide, bus-off, self-isolation protocol to protect themselves from a corrupted external signal? Imagine an entire metropolis's traffic paralyzing itself in a single instant, millions of cars simultaneously locking themselves in the bathroom and executing a safe state shutdown just to stay safe from a noisy city grid. It is an incredible, highly complex engineering problem to think about the next time you see that orange check engine light pop up on your dashboard.
It's a profound question about the scalability of these fail-safes. As our networks grow from a single car to an entire city, our safe states and recovery logics must evolve to handle not just a single battery pack, but an entire ecosystem of connected machines.
Definitely something to ponder as you hit the highway. Thank you so much for joining us on this incredibly dense, fascinating deep dive into the hidden world of automotive safety networks. Keep questioning the invisible systems around you. Keep looking for the how and the why behind the technology you use every day, and we will catch you on the next deep dive.